Hello and welcome to the fifth Tour de Tools. I have with me here my co-host Gauthier.
Hi, everyone.
During these Tour de Tools, Gauthier and me test drive tools, discuss their merits, and a lot of the times have interesting guests over. Today we have another co-host, Virginie. Virginie is the lead AI at DataRoots and has a lot of experience with reinforcement learning models. And that links to the guest that we have today. Gauthier, let you introduce him.
Yeah. So today we're hosting Jason Gauci. I hope I'm saying this correctly. So he's joining us from Texas. So it's still about 10 a.m. About like right there. So he's still fresh for today. So Jason actually holds a PhD in computer science. He has been working at Facebook since 2016. First as a software engineer and now as a senior software engineer manager at Facebook AI. Previously to that, to mention, he also worked at Apple and Google. He told us right before that he also hosts a podcast called Programming Throwdown. Make sure to check it out.
We'll add the link in the show notes.
Exactly. And today we'll be talking about a paper that he is the main author of, which is called Horizon. And that since then has been renamed to ReAgent for Reasoning Agent. And this is what he will be like presenting and talking about today. So welcome, Jason.
Cool. Thanks for having me.
Nice to hear you, Jason. So we'll be talking today about ReAgent, a end-to-end reinforcement learning platform that you are, I think, the lead developer. I don't know if that is the right title to use, Jason.
Sure, I think that's fine. I think, when I was a junior engineer, I always thought managers didn't really do anything. And then now I became a manager, and I don't have a lot of opportunity to write code. But I realized that managers are extremely busy. so it's been a really good learning opportunity, and it's been great for me to support a team of extremely brilliant engineers and scientists.
It's cool. It's cool. Can you give us a bit of a rundown on what ReAgent is, what the premise of it is?
Sure. So I have a background in working on recommender systems at the companies we talked about. At Apple, we built this thing called Proactive Assistant. And what you might not think of Apple as like a place where there would be a lot of recommender systems, but in this case, it's really a way to accelerate people's use of their device. And so one of the things in particular that I worked on was when someone got into their car, if they always opened up, let's say, Spotify or Apple Podcasts, or if there's a certain app that they always went to when they got in their car, we could learn that pattern over time, and then we could just make that much more visible and easy and accelerate that on the user experience. So you get into your car, we sense the Bluetooth connection, we just say, hey, do you want to pop up Apple Music, or do you want to pop up Spotify, right? Now, before working on all of these recommender systems at these places, I had my PhD in reinforcement learning and control theory and deep reinforcement learning specifically. And so I always kind of saw that as a narrative that needed to be kind of wound together. There's a lot of control theoretic aspects to making recommendations. And some examples of that are there's a cold start problem. So for example, we're live on YouTube, and people are going to, when they watch this video, they're going to see some recommendations on the right-hand side.
Yeah.
And some of those people are going to click on those recommendations when they're done with this episode, right? There's also going to be recommendations that didn't quite make it above the fold, what we call it, or make it high enough in this rank to show up in that list. And some of the time, the system is going to get that wrong, and those recommendations actually would have been a much better choice, right? But we'll never know because they were below the fold. That's an example of a cold start or a winner-take-all problem. And control theories had to deal with a lot of these problems since day one, right? So if you look at robotics and other domains, they've always had to deal with this. And I was seeing a lot of the wheels being reinvented for recommender systems. So I joined Facebook AI about 5 years ago to really try to close that gap and to build reinforcement learning and contextual bandits and a variety of different algorithms from control theory, but build them in a way that folks who work on recommender systems keep it in their sort of working model. Right. And we can dive into what that looks like, but keep that software engineering or that architecture that they're familiar with, but use kind of all of this control theoretic stuff that's been worked on for decades. And that has kind of culminated into what we now call ReAgent, which is a platform for doing a variety of different things: marketing, recommendations. We even do a lot of infrastructure optimization, combinatorial black box optimization tasks. Doing these things, in a kind of stable way that you would expect from like a kind of a professional system. And ultimately, where we want to take it is we want to follow the track that databases have followed, right? So if you think about databases, and this is way before my time, so this is just conjecture here, but it started as algorithms and data structures. So someone came up with let's say a B tree, a red-black tree, a variety of these different data structures, and then algorithms to construct them and keep them balanced, right? But these are pretty inaccessible. Like you have to learn Fortran or Lisp or whatever the language was popular at that time. And now we have databases where under the hood, there's still B trees, red-black trees, there's still all of these things, but a child could write a SQL query or at least start to learn how that works, right? And we want to have a decision platform that is as accessible and powerful as a database. That is the sort of North Star for the team.
It's cool. It's a nice vision.
We'll see how we can get there. That's the challenge, right?
It's a big challenge, yeah. And because you call it a decision platform, like, do you? How big of that challenge will reinforcement learning as such solve? Because there are a lot of different ways to tackle this, like more traditional supervised ways to also build recommendation engines. Like, what is your vision on that? From when onwards does it become interesting to look at reinforcement learning problems?
Yeah, it's a really good question. So I'll say two things. So one, classification and control are kind of different domains, right? And so if you think about supervised learning and how it's used to make decisions, so look at the, have you seen the show Silicon Valley? So that gentleman makes the, hot dog, not hot dog app, right? So, you have some computer vision task, which looks at a bunch of images of hot dogs and images that don't have hot dogs, and it builds some classifier, right? And now you can look at a new potential image, and it says, 0.8, right? On the probability of being a hot dog. And then you as a designer have to do something with that. And that depends a lot on the domain, right? So, for example, for the hot dog, not hot dog app, maybe you want to be, more conservative, and like, unless you're really confident it's a hot dog, you don't want to show it. And then you expect people to maybe move the phone around and get it just right, right? But then imagine like something that does cancer screening, right? So in that case, it really depends on the consequence of a false positive, a false negative, and a true positive, and what those economic trade-offs are, right? So if the effect of saying this image is cancerous or has cancer in it, if the effect of that is that we're just going to run another like relatively non-invasive test, then maybe even 0.1 is enough, right? Oh. And so the supervised learning can give you amazing signals, and ReAgent will actually use those signals just like a human would use those signals. But then someone after that has to say, take an action, set this price to this, or yes, send this message out to people, right? And typically that is done with hand-coded rules. And so that ends up being kind of our baseline.
Okay. Interesting.
Yeah, and then as far as reinforcement learning, reinforcement learning is, arguably it's the most powerful method that we have in ReAgent. But because of its expressiveness, it also results in very high, bias and variance, right? And so, you can imagine if you have to, effectively kind of like, invent or hallucinate different futures to know if one policy is better than another, you either need a really high fidelity simulator, or you're going to incur kind of both bias and variance in those hallucinations or those projections, right? We do still use a lot of deep reinforcement learning. There's tasks that just are completely, dependent on capturing that sequential nature, right? But we also have a lot of problems where it's maybe a set of decisions, but the decisions don't necessarily have a causal relationship to each other. So in other words, imagine if you were, maybe a good example is if you're playing poker and you treat, all the decisions of one poker hand as like a just combinatoric action. So, I raised, and I folded, and that package is your action. Well, then there's no relationship between one poker hand and the next. You try your action, you win or you lose, and then the slate is wiped clean, your cards are taken away from you, and you start over again, right? And so you don't have a sequential problem in that case until you introduce, your bank account and all of that. And so you can model that as what we call a contextual bandit, which is just a really, fancy way of saying, the action you take won't affect where you end up in the next state. Okay. And once you have that, you don't have to hallucinate about future states. You say, I saw this situation, I saw this set of cards, I saw this set of cards, I saw this set of cards. And, if I had folded instead, I would have seen the same cards anyways. And so that allows you to have a much more stable system, but you can't express as much. And you could continue to make this argument down the chain and make the model simpler and simpler, capturing less and less potential, artifacts, but also being much easier to interpret.
Yeah. And what led you to develop ReAgent? Because arguably you could develop all this like directly in Torch or PyTorch or whatever tooling you use for this.
Yeah, it's a good question. So, I guess you can look at, I think the most popular, going back to the database analogy, right? Like the most popular B-tree implementation is Google's B-tree, and you can find it on GitHub. It has probably, I haven't looked in a little while, but let's say it has like 10K GitHub stars or something, right? But then look at how many GitHub stars MongoDB has. I don't know, probably 10 times that. I haven't looked, but let's say 40,000 or something, right? And so they're kind of different audiences, right? And so right now, that audience of people who want to make decisions with AI, but but want to use whatever that user experience is, and we're still figuring that out. But that audience right now is underserved, and so ReAgent is a scaffold upon which we're going to build that experience. So that's kind of looking forward. Looking backwards, or looking at, say, at the present, we have a lot of pre-processing. There's a lot of on the serving side, you actually want to have what we call a stochastic policy, which means you want to occasionally choose the action that we think is the best, but sometimes choose the other action. And that gets back to that YouTube analogy where, if everyone saw the same things recommended, we'd never know what that 11th item would do. But if some people saw a shuffled order, or if everyone saw things a little bit shuffled, then we wouldn't have that problem. And so we have a thing called ReAgent Serving Platform, which lets you inject kind of randomness into the system that isn't totally disruptive, but at the same time allows us to extract a lot of what we call counterfactuals. So it allows us to answer a lot of those what if questions much easier than if the policy always did the same thing every time. So when you combine kind of this serving layer with all the data transformation, the training, and then closing the loop, pushing the model out to the serving layer and doing all that bookkeeping, that right now is ReAgent. And in theory, I don't think we have anyone doing this yet, but in theory, you wouldn't even need to use any machine learning. You could have the serving layer with the structured noise and just a hand-coded policy.
Yeah.
And so we've done this to draw comparisons, but you could even do this in production, and you would still get all the benefit of the counterfactuals without even needing a model.
It's interesting. I have the feeling that when you look at more, let's say, traditional supervised methods, there's a lot of tooling out there to easily set up a quote-unquote decision system. Think about versioning of your models, these type of things. How do you set up a good CI/CD pipeline to deploy these models, to test these models? And for reinforcement learning, I think this is a bit the challenge that ReAgent tries to solve, but a lot of that is still like, if you ask a random machine learning engineer, like, what is the best practice of setting up a good MLOps flow with a reinforcement learning model? Like, I don't think that there are a lot of people that directly know how to tackle this. I think we're in an earlier stage with reinforcement learning models than we are with supervised, more traditional supervised methods.
Yeah, I totally agree. I think that, and in a way, it's a huge opportunity. It's very low hanging fruit because we will do all of these really complicated, multi-node, EA-SGD, training on thousands of machines, these massive supervised learning models to predict some signal. And then at the end of the day, someone will just take that signal or take 3 of those signals, add them up, and then sort. And then that's how the serving system works, right? And there's just so much opportunity right there. And we've been trying to squeeze so much out of this other rock, right? So I think that it's very foundational, and these things are always scary. I mean, I think one of the biggest things people on my team are apprehensive of is that maybe the time isn't right, like it's too early, or people aren't going to adopt this, right? I think a good analogy is, I used to look at the old Atari games and say, oh, there's just one person or maybe 2 people who made a whole game. So they created this kind of work of art just by themselves. And now when I look at video games, they're just these massive things created by thousands and thousands of developers. Or I mean, not all of them, but a lot of them. But at the time, they weren't sure if that medium was even viable. And in fact, I think Atari or one of these companies went out of business, or at least a lot of them struggled, right? So it's foundational, which is scary, but also really, really exciting. I think the thing that really, solidifies it is that everyone needs to make decisions. Every company needs to make decisions, even every mom and pop restaurant. Like, we're all going to go and have lunch. And if we're not making our own lunch, or even if we are, we have to make decisions about cost and price and all of that. So everyone's making decisions. And it's just a matter of like, how can we make those decisions better? How can machines sort of empower people to make better decisions and to really help them interpret the decisions they made? So I think the opportunity is there. It's just a matter of finding out how we can, really empower people. What does that API look like? Like, what is the equivalent of SQL for a decision-making system? Like, these are all open-ended questions that no one has answers to yet.
And maybe because this is all very new and not super common yet, do you also provide in a ReAgent, or is it the intention to do common use cases, example like a chatbot or a dynamic pricing, or like those very minimal examples? Because I think there is also a lot of thinking to do in target creation?
Yeah, it's a good question. So, we do have an example where you run a sort of very simple e-commerce site, and we have a simulator which can simulate customers coming and visiting your e-commerce site, and then we show how, as someone moves from one approach to the other, how that kind of changes the expected value of their model. So, I think it is there. I think the part that one thing that we've always wanted to do, and we'll probably get to it, sooner rather than later, is, integrating it with the rest of the open source community. I mean, we're built on top of PyTorch and Spark, and so we're extremely thankful for those libraries. I'm sure almost everyone here has used Spark. It's amazing. You can run SQL on CSVs and run SQL on files that are enormous, and it does the right thing. And PyTorch also, PyTorch started the whole dynamic computation graph. I remember using, early versions of TensorFlow and then later Caffe2, where if there was an error, you actually had to create sort of an operation that kind of printed something. And half the time, like, the error would, be, out of order and your print wouldn't show up. And it was very difficult to debug. PyTorch with their just-in-time compiler, and I think that also made its way into TensorFlow recently, is amazing. With all that said, I think we're not ReAgent right now. There's no hook to hook it into, let's say, a CRM, or hook it into a system that delivers notifications or marketing material, or a system that does pricing, right? And so that, I think, is something that we need to build out. I think right now, people are having to, create really large volumes of data on some data store, run ReAgent, and then figure out how to get the serving platform integrated into their serving system. There's just a lot of really complicated engineering that has to go on right now. Now, for many people, they're early adopters, and there are many companies out there that have had good success with ReAgent, which is great. And they've spent a lot of time and energy to do it, but they got a good reward out of it. And so I think, one thing to mention is, even though we have this vision of making it super accessible, it's still really useful to a lot of folks now. But I would definitely expect folks out there to put your engineering hat on, because it's still pretty early. It's kind of like using bee trees in the 70s or something.
Yeah. Okay. This was actually one of my questions, because you mentioned this already a few times, that you're trying to bring in a SQL-like interface to something as difficult as a bee tree, right? So the same way you're trying to do this for reinforcement learning. Where do you think you're at the moment, and what maybe you see as the next steps to actually reach that goal? Of course, it's very long range goal, but yeah.
Sure. Yeah. So where we're at right now is we've gotten a good handle on how to do offline reinforcement learning. And so this, if you look at the work that we did on Go and all the follow-up work that folks like OpenAI have done, a lot of it is with a really high fidelity simulator and no sort of sim to real challenges, right? So if you do well in the simulator, you did well, period. If you play great Go in the simulator, you can play great Go in real life. That combined with the fact that the simulator is also, deterministic, and it's very simple. So in effect, you could think like the hardest part of Go, if you think about historically, the hardest part of Go has been actually taking what someone wanted the Go players to learn many years ago, which is, how to arrange armies in a war and fight, a battle with troops, and reduce that down to these stones, right? So that sort of knowledge representation or representation learning was all done by people, and that there's a lot of complexity there that you can easily skip over, right? So in the real world, you're going to not have a simulator. Your problem is going to be definitely partially observable. You're not going to be able to read the minds of your customers, right? And so a lot of the canonical algorithms are going to struggle. And we saw this. I mean, when we started the project 5 years ago, we saw that a lot of the state-of-the-art algorithms just were not working at all. And so we learned a variety of lessons from that. I think one of the lessons is that people want the policy to be stable. So in other words, imagine a situation where you have some goal. Let's say the goal is, I'm just making something up, revenue. And so every day you roll out a new policy, and every day that policy gets the same amount of revenue. Then from your perspective, it's great. It's very consistent. But actually, the customer is telling you the policy is wild. Every day it has a completely different strategy, and just coincidentally, it's landing in the same spot, right? In terms of that goal that we tried to measure. So one of the things we did early on was we started with cloning the current policy. So whatever generated this data set, let's clone it and see if we can suggest the same action. So when the logged policy, when it says take action 1, we say take action 1. It says take action 3, we say take action 3. And if we can't do that, let's fire an alert saying like, we can't seem to recover whatever this decision system is. If this is our system yesterday and we can't reproduce it, that's a problem. And that happens because of bad data, corruption, machines that behave erratic, et cetera. After we do that behavior cloning, we call that kind of our warm start phase. Then we will start training, and then we'll be sort of biased in the region of the current policy, right? And you can imagine developing like what we call a trust region, or saying, if we start recommending things that are different than the logged policy very often, that's a time to stop training. We're starting to hallucinate a lot, and that could be great, but it could also be catastrophic. So, let's stop training. We're going to roll this policy out today, and then tomorrow let's pick up where we left off. Yeah. And so what we see with the ReAgent is there's actually 2 loops, right? There's the training loop, which is happening every day, but then there's this broader loop of collecting data, learning from those mistakes, and then repeating that. And so we have models that have been in production since 2019 that are still getting better, which is actually pretty remarkable. It's something we didn't really expect. And so handling sort of the online offline component, also doing really well offline evaluation. I can dive into how that works. There's basically 2 approaches. The first approach is to build a simulator. Like given a data set, you can always build a simulator from that data. And so we do that automatically. Now that simulator itself will have errors. And so, you'll never be able to trust that evaluation 100%, right? Yeah. It'll always have some bias. There is actually a way to do completely unbiased offline evaluation. And when I first heard this, I thought that it was like a myth or a joke or something. I mean, I didn't really understand how this was possible. But intuitively, the way it works is like this. And I'll explain it with an extreme example. Let's say you have a binary reward situation. And it's a contextual bandit. It's not a reinforcement learning problem. So you're given a decision, you choose, I would say the action's binary too. You're given a decision, you choose, heads or tails, and then you either get a reward of 1 or 0. And then it moves on to the next decision. And so you have this huge data set. Here's the decision, context. I chose heads, I got the reward. Here's the decision context. I chose heads, I didn't get the reward, right? So you have this huge data set. And let's say you train a model, and that model, every time you get the reward, that model chose the same action. And every time you didn't get the reward, the model chose a different action. Yeah. So in that way, number one, the new model is guaranteed to be as good as the old one, right? Has to be. And number 2, the model's probably better. I mean, probably one of those times that old model made a mistake and the new model corrected it. So in that extreme example, you can say something completely definitive, right? Now, moving away from that and kind of relaxing that a bit, this is where that randomness is really important. So we'll have a variety of different algorithms and this is all in the serving platform, to inject some noise and some randomness into the decision. And so what that means is even when the model thinks this is the right decision, it's still going to make the other one a few times. And so our data set is going to be full of these, we call these counterfactuals. And from all of those probabilities and those counterfactuals, we do a pretty good job of saying, this model is better than this one, guaranteed, 99% confidence. And so, that method's now the way I've described it, that method sounds like a silver bullet, but it also has challenges. It's more often than not going to say it doesn't know. And so the reality is you have to use all of these methods and look at it kind of qualitatively. And so one of the places we want to take it is to make that more mechanized. But I think we're definitely ahead of everybody else, at least in the open source community, on having offline evaluation that is really robust, that's battle tested, and that gives you a lot of really useful feedback.
Yeah, that's interesting.
Maybe, or do you want to go, Bart?
Well, what I had in mind and linked a bit to the evaluation, like, is there a notion of explainability in ReAgent? And the reason why I'm also asking is that, let's say, intuitive, like, or how we see this a lot of the time is not only from a technical point of view, but we need to explain how a model works, why a model works. And I have, well, maybe it's a bit my personal opinion, but I have the feeling that it's easier to explain the way a reinforcement learning model works versus, let's say, a more classical recommendation engine. Because in the end, a reinforcement learning model is very close to how things, people, animals learn in nature in the end. And that is a quite intuitive way to explain it. And if you look, for example, about like what is your target that is being optimized, it is often it's relatively easy to explain in business terms, not necessarily technical terms. And of course, like the model itself, how it learns these things, there's a big black box component to it, but how it does this is quite intuitive.
Yeah, it's a really good question. So if you look at model interpretability in general, even in supervised learning, what we find is, there are methods like excitation, backprop, and some of these Lime and some of these other methods that try to say, kind of why the system did what it did. And those are super useful, but in recommender systems, they tend to be less useful because a lot of people don't even know what the features are anymore. Like, they've developed the features over years, and it's like, okay, well, the reason why this probability of someone clicking on this email is high is because, feature F134 is high. And so and to your point, it ends up being the supervised learning, feature importance ends up being more useful in a mechanized way, where maybe you automatically take the top 1,000 most important features and then train the model on that. And so getting, good human interpretability on even supervised learning is kind of an open problem, right? I think it's something that's really exciting. The nice thing about reinforcement learning, or just decision making in general, is that you can focus on explaining the decision, and you don't necessarily need to say, well, this feature caused this decision. More just that if you have two policies, how are those policies' behaviors different? And so that, I think, is more accessible and easier to do. So yeah, I think that is something that ultimately will be easier for us. So looking at what there is now, so one thing to keep in mind is often we don't even know what kind of problem we have, because what was done before was done by hand, and so people don't necessarily know. They don't come to us and say, I have this contextual bandit for you to solve. And so we have this thing called the domain analysis tool. and it looks at these large volumes of data and trains a variety of models to try to predict what class of problem exists here. And so we might learn something like, we can't solve this problem. Like that's actually one of the outputs, which usually means there's a problem in the data, right? We might also learn, the value of doing reinforcement learning is this much. And so just do a contextual bandit. Or we learn that the contextual bandit will just not work. So to give you an example, there's the canonical, cart poll. So if you've ever gone to OpenAI, Gym or baselines or any of this, you'll see this, it's like a vehicle that operates in 2 dimensions and that can go left and right. And there's a pole that's, this inverted pendulum that's coming out of the car. And the goal is to keep that pole balanced. And so, the pole has a tendency to want to fall over because it's unstable. But if you balance the car right, you can keep it balanced indefinitely. And so actually in the oh gosh, I haven't been there in so long, but in San Francisco, there's Exploratorium. In the Exploratorium Children's Museum in San Francisco, they actually have this at real life. So they have this cart pole that in real life, like it's really cool, and it's big too. I mean, like if you live in that area, or if you have a kids museum around you that has that, it's really cool to watch. Yeah, even in that, if you were to look in that environment, the way cart pole is set up is you always get a reward of 1, because every time your system is alive, the pole hasn't fallen over. That's good. And so what you're trying to do is like have a really long episode. The reward actually is totally irrelevant. And so if you use let's say a contextual bandit on cart pole, it's not going to be able to do anything, right? You need reinforcement learning. And so you can build models that will tell you that, and building those models is actually easier than solving the problem. So we have this domain analysis tool that gives you a variety of different information about your problem, and then the thing that we do on the interpretability side is we look at the action probabilities and the action distributions. So that's what we have at the moment, and that turns out to be really useful. So for example, if the hand coded, the policy that is in production right now, takes this action 80%, let's say it's binary, takes this action 80%, this action 20%, and reinforcement learning does the opposite. That's like pretty concerning, right? I mean, it either means that there's huge headroom here and we found it, or more likely that there's a problem somewhere. And so, right now, most of our interpretability is focused on looking at divergence and trying to keep things stable. And that ends up being just extremely useful to a lot of folks.
Yeah, that's interesting. And I think like interpretability in general is still like a very active research field. There are no solvable solutions. And typically like how it's, let's say, sort of solved is, even if you cannot fully understand it, you need to monitor it. You need to make sure that your performance stays in a range that you expect it to be. And in this, because you touched upon it a bit, like performance evaluation, like, do you have something built into ReAgent that allows you to easily evaluate the performance of a new policy before you accept it and potentially deploy this policy to a production system?
Yeah, it's a good question. So just to set this up a little bit, look at if you look at most of the libraries out there. So look at the thing that trains like OpenAI baselines or something that's training in simulation. Every mini batch, there's only one model. So the model that is, playing the game is the model that is being trained. And so every mini batch, you're kind of updating that model. And so if that model ends up, let's say, in a really bad state for one mini batch, it doesn't matter. It makes one mini batch worth of bad decisions, and then now it's good again, right? To frame how it works for us, so just last week we made 1.5 trillion decisions, and this is just at Facebook, right? And the model updates rarely. I mean, different teams have it at different cadences, but let's say once a week or once a day, right? And so if you just happen to be on that bad mini batch, then you're going to make billions of bad decisions, right? And so we just can't do that, right? And so all sorts of like online training and all of that kind of goes out the window for so many reasons. Imagine you get paged at 4 a.m. and it's, oh, the Bellman equation is misbehaving, you just have to like rub your eyes and try. It's just impossible. So we need to have like total confidence in a model before it goes out. And there is an amazing team that we work with called the Predictor team, and their whole job is to serve all kinds of models, supervised and reinforcement learning, et cetera. And they do get paged all the time because it's such a massive endeavor, right? And so hats off to them. But on our side, like our goal is that every model goes out with, a good sanity check, right? And yeah, the offline evaluation we talked about is a big part of that, and also measuring divergence between what we saw in the data and what's going on right now is another really big part of that. And it's sort of like playing the long game. One nice thing about machines just in general is that they're tireless, right? They're tireless workers. And so, we will roll out a policy every single day, there is sort of like freezes on really critical days where, but let's say 300 days a year we'll roll out a policy. And so we don't have to get the optimal policy on day 1 or even day 10 or even day 100. And so getting that slow climb and stable climb is really what we want to do. And when we're developing the model, a lot of care is taken into looking at those dynamics. Another thing we do is we look at a variety of different metrics. And so even metrics that might not be considered by the reinforcement learning model, we'll have another model that predicts the effect of the policy on those metrics. And so, you can imagine that there's a multi-objective problem. You have 4 objectives you're really interested in maximizing, but then you have another 13 sort of guardrails where you just want some homeostasis, right? And so, I wish we could get to the point where we could just handle all of that autonomously. We're looking into how to do reinforcement learning with constraints and how to do that really well. That's an active area of research for our team. But at the moment, what we have is a really stable kind of monitoring environment. And that's been really, really crucial for all the folks that are using it.
Cool.
Right. I look in the chat. So there is Xavier Hering, which is asking a question. Could you go in more details on the domain analysis tool? And he would love to learn more on how it was created, if it has been published, and also how you compare a sim model towards a real life model to see if the real world model is matching the performance of the sim.
That's a long question. Those are 2 questions.
Yeah, there's a lot to unpack there, so I'll try my best. So maybe the domain. Go ahead.
Tool. Yeah, go ahead.
Yeah, the domain analysis tool. It is definitely out there. I think we do need to work a bit on our external documentation to get it up to speed. One really cool thing that we have is we have a 2-way sync between GitHub and our internal repository. So, that's good and bad. I mean, maybe we should start making releases, right? Because you never know what you're going to get. But on the flip side, it also means that we get to push things out to everybody right away. There's no delay. And the domain analysis tool is definitely out there. So yeah, it's getting a little bit onto the technical side, and I can move on to the other parts of the question. As I mentioned, the contextual bandit is one where no matter what action you take, you end up in the same state. And so imagine creating a neural network that learns what we call the transition function. So it says, given a state and an action, it predicts the following state, right? Mm-hmm. So that's a purely supervised task, right? It's not trying to answer any what if questions. It just, if it got the state right, that's great. If it didn't, well, that's, there's some loss there, right? And so you can look at the feature importance using the supervised learning, feature importance, things like excitation backprop and bootstrapping and things like that. You can look at the feature importance of this transition model. And if none of the action features are important, well, then you have a contextual bandit, right? Or if they are important but not very important, then maybe you should use a contextual bandit, even though there is something there, but it's just not worth all the extra bias and variance, right? So that's ostensibly the domain analysis tool is a variety of what we call, and what Schmidt-Huber called, world models, which are models that are trying to learn these dynamics directly, right? So then the question is, how do you deal with all of these things, the offline evaluation, the world model? How do you deal with them when they're wrong? And that is, we spent an hour yesterday among the team just talking about that and brainstorming exactly that. It is a really big problem. And honestly, we probably spend, a good % of our time just as at least right now, just trying to, figure out what to do there. There's a variety of different ideas. One is that, we noticed a lot of the times these models are, directionally accurate, which is kind of what you would expect. So if this new policy is better than the old one, it's usually pretty good at saying that. What is not good at is being really specific in absolute terms. And so what that means is you can't derive anything from the off policy. Like, think about architecture search. It's like deciding how many hidden nodes should be in your network. So if you're doing supervised learning, neural architecture search, there's a variety of different techniques that can be used there. You can do gradient-free optimization, right? You can do grid search, just try a bunch of different networks, right? And then you can measure something like normalized entropy or F1 or something and say, yeah, this architecture is the best, or this architecture is the best and saves the most CPU resources, right? It handles that trade-off in a way that we like. But for reinforcement learning, if our metric itself is only directionally accurate, then you can't do neural architecture search, because what it's going to do is it's going to find the architecture that best sort of exploited the problem in your offline evaluation. Like, whatever the hole is, you'll find the architecture that exploits that logic hole. And then when you launch that model, it won't actually be that much better. It might still be a little better, but you're not going to get what you expected. So yeah, we have two ideas that we're pursuing in parallel. One is trying to build kind of a sim to real, translator. So something that tries to predict the gap between sim to real, between sim and real. And so, we would generate a bunch of hypotheticals, we would launch them, we would see a gap, and then we would train a model to try and predict that gap. That is one thing we're kicking around. Another idea is to just be better about online and offline, and being better about experimenting online and making that more fluid. And so that's, in a way that's sort of like conceding defeat, but there's definitely some environments where your offline estimate can only be directionally accurate. We've seen things, especially when the thing that generated the policy isn't ReAgent, and you're comparing it against ReAgent. Like, in a lot of those environments, we're just never going to be totally sure. And so it's really then, in these initial phases, it's really about trying to collect as much important data as possible.
Yeah, this links back to what you were mentioning earlier. It's just also super difficult to build a high fidelity simulator.
Yep. Yeah, absolutely. And it's you don't really know if you have one either, so until you deploy it.
And if you then look at let's say cost efficiency, sometimes it's less costly to let's say in a cautious way actually try this on a production system.
Yep.
To see if it performs.
Yeah, I think the randomization is a really interesting area too. So I remember Yahoo News had a sort of 1% holdout. I remember just talking to somebody who worked on Yahoo News, where for that 1% holdout, they got completely random news. And that's you just hate yourself if you're in that 1%. You just get literally just random news all the time. Hopefully they rotated it or something. But But yeah, that is extreme. And actually, it turns out that that is not very useful, because a random policy is so far from an optimal policy. You would think that you could learn so much from that, but in practice, you actually can't, because that gap is so large that you quickly end up in a position where the data is not useful. And so there's a lot of research around how to do randomness in a structured way, and how to log the effect. So for example, I'll give you an example. Let's say you were ranking. So in ranking, you might say, well, instead of putting this item first, I'll randomly either put this item or the one next to it. And then now I've put that item there. Now I'm going to have to fill in the rest of these items, and I'll just repeat that process, right?
Yeah.
And that seems straightforward, but then the problem is you have to measure what's the probability that I picked all 8 of these items, the combined sort of probability. And that ends up being really hard to calculate. At best, you can do some kind of Monte Carlo simulation, but you have to do it on every example, and it's just not practical. And so without those probabilities, the randomness just by itself is not that useful. Because again, we're not doing that much randomness. So we need those probabilities so that when we do something that's exploratory and the old policy gets it wrong, that we make a big correction, because there's all those other times that we did it the other way, right? So one thing that we invented, and there's a paper that we published, I think it was last year or 2 years ago, was this idea of Frechet randomization. And this was a trick where, getting a little bit of a data science geek out here moment, but if you take like normally distributed numbers and you add them together, you get another normally distributed number. So imagine you have a random number that's centered at 1, you add it to a random Gaussian random number that's centered at 2, you're going to get a Gaussian random number that's centered at 3. And in this case, what we're doing is we are ranking. So we're making several decisions in sequence, and we want the product. So we want the product of all those probabilities. Wouldn't it be great if there was a distribution that worked that way in product, where if you multiplied the distribution by itself many times, you would get that same distribution? And there is. It's called the Frechet or the log-Gumbel distribution. And it's close enough to the Gaussian distribution that we were okay with how the tails looked. And so we add this Frechet step at each step of the rank, choosing each item in the rank. And then we can just multiply all those probabilities, and we get the Frechet probability of the whole slate or the whole session. And so that was a trick that we built a couple of years ago, and it's in ReAgent, and we're using it a lot today for our ranking problems.
Yeah, that's super interesting.
Just quickly, because there is a small delay. Xavier, just thank you for answering the question, and is looking forward for blog articles and documentation. Just quick note.
All right, cool.
On you answering the question, but please go ahead, Bart.
I lost my point that I was trying to make. But I remember again. So it is very interesting that you're like again, the paper that you're publishing, ReAgent is open sourced. Like, has this been what is the rationale behind open sourcing? Is it something that is standard within the culture? Has it been a conscious choice to say that ReAgent really need to open source, or how did this come to be?
Yeah, it's a good question. At the time, the reason for open sourcing it was because I wanted something that was permanent. So if you look at like SciPy, so SciPy, actually, there have been times, and I don't know why this happens or how this happens, there's been times where my machine has had to build SciPy from scratch. I don't know why that is. I'm not an expert on Python packages, but, and there's been one time specifically where a Fortran file failed. And I thought, wow, SciPy has Fortran code in it, in 2020. And if you think about it, yeah, it's like that Fortran code outlived, Sun Microsystems, right? It outlived SGI. Like, it probably was there before SGI started, and then it outlived them. So it's completely eclipsed these companies, right? And so that is sort of part of this sort of eternal conversation that we have with nature, right? I mean, it's kind of remarkable that it's still there. And maybe it'll get rewritten in C. I mean, I wouldn't, even if it gets rewritten in C or some other language, the idea is still there, and maybe the comments will stay there or what have you. But I felt like we're on the cusp of something really pivotal, and I wanted it to last forever. So that's ultimately the reason of open sourcing it. Now that we've found a lot of good utility, we have other reasons for open sourcing it. And we're helping a lot of people, a lot of companies all over the world, which is awesome. I mean, it's getting into SAP, so that I think is going to open up a lot of areas. And so yeah, I think that is showing to be really nice as well. But yeah, ultimately, it'd be nice if this became like the MySQL for decision making, and so yeah, I'm really fortunate that the place I work was cool with that, and so they're big fans of us continuing to keep it open source, and I think there are challenges with internally we have our own version of Spark. We have our own version of HDFS, which is a total rewrite. And so, at some point, the code does have to differ. Like at some point, the internal version has to do something different because it's a different platform, right? And so, it can be a little frustrating trying to, have a system that can work in these two modalities effectively. But I feel like it's worth it because the benefits have been great, and talking to folks who use it and stuff has been a real pleasure.
Yeah, that's really cool. And do you already have like external contributions to ReAgent?
Yeah, it's interesting. So we do have them. I think that, and I know for a fact that there's a lot of people who use ReAgent and don't contribute back. I think there's a variety of reasons for that. One is, it's still pretty early. And so the things that people build on top of ReAgent are very specific, and it's usually ugly because it has to hook into other libraries. And so rarely do people have something that if they do contribute back, it's going to be either, fixes, or it's a addition to our pre-processing or one of our algorithms. And so when someone comes in and if we get a like, oh, you have this hyperparameter set wrong from like so and so at Deloitte, like we can kind of feel like, okay, this person must be using it to have known about this really esoteric error, and so that is good enough. And I have talked to companies that are using ReAgent and sat down with them, but yeah, I think the nature of ReAgent right now is one where people aren't contributing that much back, at least not as much as they're as much as they've built on top of it. And I think that's totally natural. I just think I think when we get we need that sort of DSL, like that SQL type thing, and when we get there, then we can see this really explosive like Cambrian growth in the community. But until then, it's just good to know that people are using it.
Yeah, quick, like I do have another question on this, like because you mentioned you use it internally, you expose it, and you see a lot of use at clients. Like, how do you then do a priority between what should enter the project? Like, is this only purely based on the needs at Facebook, or do you really take into account like outside needs, basically? And let's say from somebody from ACP now telling you like we really need this feature, for example, to make it work. Like, what's your decision process there?
Yeah, it's a good question. So, yeah, so internally in the team, we really have sort of 4 kind of pillars, and we try to make sure that we kind of treat all of them kind of equally or equitably, right? So one pillar would be our platform, and that's kind of keeping it stable. It's really hard to know what stable means externally. So at the moment, it's really just keeping it stable internally. We have so many folks depending on it, and so that is a whole effort in of itself. We have our customer pillar, where usually, when we have a new idea, we're always writing the papers post hoc. So look at like the Frechet thing that we just talked about. We had that idea, we found a customer, internally, like a team that needed that idea. we showed that it worked, and we spent a lot of time with that team to show that it works. And then, we write the paper and we democratize it, right? So there's that customer pillar for some of these new initiatives. Then there is a research pillar where we're trying to come up with sort of how do we do auto RL, right? How do we do better offline evaluation? And then the fourth pillar is our service pillar, right? And that is, it's a combination of things like, recruiting and advertising our team so we can get kind of more really talented folks, our on-call responsibilities, and then also, our commitment to open source and making sure that we're being sort of a good citizen there, right? And so, there is sort of space allocated for that. And I think, if we get to that point where we're getting, tons of contributions coming in, then we're going to have to, it'll become like more of an economic problem, right? Where we have scarcity and we'll have to figure out what to do. At the moment, we're still kind of bootstrapping the open source. And so we haven't had to tackle that quite yet. But, when I look at PyTorch and other teams, at Facebook, they've done an amazing job of fostering that open source community. And so we'll leverage all of the lessons learned from those teams. So we're all in the same organization, so we can all help each other out.
It's very interesting. Very interesting. And indeed, like it's also, of course, a natural evolution. It's very logical when you're in the beginning phases of building something that the priority goes to the features that you actually need, and not the feature that someone else outside of your company needs potentially, which is normal, I guess.
Yeah, and once we learn to generalize, then I think we'll start getting a lot more of people adding more to the system externally, and then we'll have to figure out how to merge all of that.
Yeah, exactly. Yeah. So how do you make sure that it's easy to contribute without impacting the core? Like for example, one of the things that I know, like you mentioned it, that you use Spark a lot, which is of course like a very strong dependency. Yeah? And ideally, data processing, you would be able to choose that. Of course, like Spark is being used very widely, but potentially someone would like to use something like Dask or something. And then it would be nice at some point that you can say, okay, these are not necessarily part of the core, but these are plugins that you can interchangeably swap out, and people can contribute with their own plugin.
Yeah, definitely. I mean, even, internally, our end-to-end tests are using Spark. And so we'll end up getting test failures because the Spark cluster is too busy. And so yeah, I mean, the system right now is not as modular as we would like. The challenge about modularity is then keeping everything in sync. So it's like, how do you know the Spark code isn't broken unless you're testing it? And, so those are some challenges we're struggling with right now. I mean, if someone knows of like if someone invented like an API that spanned, Dask and Spark or something like that, I mean, that would be amazing. I don't even quite know what that would look like. I'm actually surprised there isn't like a SQL interface to pandas, or something like that. I mean, I feel like there's all these kind of disparate technologies, and maybe there's some way. Of course, you unify this, and what you end up with is like an n+1 technology, right? And so you have to avoid that pitfall.
That's the thing, yeah. I think what's it called? Apache? It's by Google.
Yeah, it is. I can't find it. No, it's a Google service. Is it maintained by Google?
I think so. But it basically tries to unify this, and it's sort of like it uses Spark as a potential execution engine, but you can also use a local or their data flow service, I think.
No, it's
Oh, cool. Yeah, I mean, for our open source tests, it actually just runs Spark locally, and I think there's this thing we have called it's a thing we're using called SDK Man, which is kind of like a Anaconda, but for Java. And so you can actually get a Spark environment kind of containerized. And so we find that to be pretty useful.
Apache Beam. Exactly.
Oh, nice. I've heard of Beam. I haven't really done a deep dive, but
yeah, but that tries to make a bit of an abstraction of different data processing engines. But
and that's actually Flink, Spark, Python, and Go.
Yeah.
I don't know. Well, yeah. supports multiple things.
Yeah, I mean, if anyone feels ambitious and wants to write our pre-processing, rewrite it in Beam, we would definitely accept that pull request.
Can imagine. Okay.
Very interesting.
Yeah, extremely interesting. Virginie, do you, maybe, I don't know, like if you have other questions, something you want to add? You're muted.
No, I think we touched upon a lot of very interesting things. Now, maybe an idea would be to test this, Bart, Gauthier.
We should. So for someone that wants to get familiar with ReAgent, should you start testing it?
Yeah, I mean, it's a good question. So, we have, reagent.ai. That's our landing page. We have a tutorial there with the e-commerce example. I actually originally, the e-commerce example is, in this example, you have, I think it's bacon and ham.
Yeah.
And there's certain people who are bacon enthusiasts. And originally, the name of the whole project, of this whole example project, was called Hamazon, but the marketing department at Facebook made me change it. So now it's completely out of context, and no one really understands why there's bacon and ham. But but you can kind of walk yourself through that, and it kind of walks through training the model. I mean, also take a look at the end-to-end tests. I think that's a good way to see kind of how the system works. I think one of the challenges with our end-to-end tests is and I think we talked about this a little bit in the pre-show, is the the pre-processing ends up kind of in the beginning, if you have a totally random policy, then the pre-processing is going to be kind of very heavily biased and biased in a way that helps random models and not necessarily optimal models. And so that is a really interesting challenge where, in supervised learning, you just give it as many features as you want. Give it millions of features, big data, lots of features, big models, and just turn up the regularization and you're good to go. But for reinforcement learning and just control problems in general, the more features you give it, the harder the problem becomes. And so the feature importance is really important, and the pre-processing is really important. And so I think that to start off, I would probably start by figuring out which features are the most important. And you can run our domain analysis tool. Also, if you're pretty adept at PyTorch, you could just build this yourself, where you pass in your state, your action, you try and predict the next state. You also try and predict the reward. I mean, you could even, I don't think we do this now, but you could even imagine a triple loss where, given the state in action, you try and predict the next state, the reward, and whether the episode terminates or not. And you could just have one model that does all of that. And then learn some stuff about the problem, pick the most important features from that model we just talked about. And then train a simple model with just the most important features, where maybe you set the pre-processing by hand using what you know about those feature ranges and the distributions. And that would be kind of an easy way to kind of get started with the system.
Cool. And let's say when people really want to adopt ReAgent and want to deploy this at scale, is there already something available to easily do this? Like,
yeah, it's a really good question. So we have this serving platform, which is a C++ library, and internally, we sort of inject this into a much bigger serving. Well, there's many serving platforms at Facebook, and this library is kind of injected into there, right? But for open source, it's effectively becomes like a standalone service. So we wrap it in some C++ like microservices API. And so you can either run that directly, although keep in mind it's not designed for high throughput, because that wrapper is I think it's single threaded. Or if you already have a serving system, you could put this in there, as long as you have a way of kind of linking in the C++. So that, I think, is one way to do it. Another way I've seen this done is where people use ReAgent and then they push the model to AWS. So as part of the training script, and then their serving system is just polling the AWS directory for new models. And they basically build the serving system by hand. That's another way to do it. But yeah, the serving platform hopefully is a thin enough and abstract enough kind of shim that people can insert it in there. And one of the things that I'd like to see us do this year is build like a more end-to-end example that actually puts the serving platform on AWS and makes web requests to it. Right now, in the example, it's all just making curl requests to localhost. And so it's a bit of a fictitious environment.
So for potential contributors listening, that might be a good example for them to build in the documentation.
Yeah, a lot of folks ask me, because of the Programming Throwdown podcast, a lot of folks ask me, how do I get started doing programming, or how do I get a job doing programming? And taking one of these open source projects and doing something with it is a really good way, maybe even the best way to do that. I know a lot of companies will look at your GitHub account as part of your resume, and so you'll show a lot of good activity there. And I think getting ReAgent up and running on something like Azure ML or AWS, I think would be a fantastic project, and we'd gladly accept, even if it's just a documentation file or something, we'd gladly accept that PR into the repo.
Oh, into the repo, even not even as a separate project, right?
Yeah, no, we're pretty open-ended. So I mean, if someone has some kind of wrapper, we have a scripts directory, and we might have to massage it a bit, but we're more than happy to put almost anything in the repo if it's productive.
I think Gauthier here's opportunity.
Nice.
Okay.
Always interested.
Thanks a lot, Jason. Do you have anything else that you want to share, Jason? I think we're a bit questions.
Yeah, I think definitely if you have any follow-ups, you can reach me on Twitter. Neural Nets for Life, the number 4. And this was back when no one thought neural nets would do anything. I started using that as my handle. We couldn't even get our neural net paper into NIPS, which has neural in the conference title. So I was getting my PhD. No one believed in neural nets, and so I did. So I called myself Neural Nets for Life. So you could always tweet me there. You can email me, I'd love to see folks using the platform. It's, as I said, it's early stages, which is you're going to face some challenges, but it's also, I think, the really exciting time. Like, think about the App Store. Now the App Store is so flooded, it's very hard to make a popular app, right? And this is, I think, something that's so greenfield, and it's because it's difficult to use right now. It's also really exciting to be kind of there at the beginning. And I'd love for people to check it out and join us on the journey.
I think it's definitely a journey. This is at the right time. Huh? This is at the right time to make a big impact and to have a project that potentially grows exponentially in the future because you're this early. And there is a need for this, clear need for this.
Yeah, definitely.
Thanks a lot, Jason, for sharing your views.
Cool. Thank you so much for having me on the show.
We'll make sure to share your contact details in the show notes, and also to your own podcast.
Exactly.
The program.
Yeah, definitely. If you know anybody, folks out there, this is my guess is most of the listeners out there are pretty into programming already. A lot of working professionals, but you might have someone out there, or you might be interested in learning about kind of the field and talking to some of these people who invented programming languages and that whole stuff. So if you're interested in any of that, check out Programming Throwdown. We've talked to a variety of different programming language inventors and framework inventors. And if you know anyone who's really pushing, a new framework or a new programming language, definitely connect us, and we'd love to have them on the show.
Nice. Thanks a lot, Jason. That's it for this time. Next time we will see Thomas de Klerk, one of the founders of Cumul.io, and that is on the 4th of May. Thanks a lot. See you next time.
Thanks.